you will have the center to center, center line to center line of the columns. And this can be the distance from the center of the column to the other column. You're going to have the beam size and the column size can be given to you. Now you need to come up with this A, B, and C. And you have a range. And this range is going to be based on the properties for the moment frame itself. Once you set A, B, and C, and of course you're going to pick good numbers, avoid quarter of an inch, avoid half an inch. It would be good if you just do to an inch for the A, B, and C. If you really have to go on half an inch, I'm okay with this. I mean, if you have to, but try to avoid it if possible. And then after this, you need to figure out the R, the radius for the cut. Let's give you this radius for the cut. Let's give you the radius for this circle. And then after that, you figure SH, which means the hinge location. Hinge location now is going to be from the center of the column. Once you find out the center of the column to the hinge, you can find out L prime. L prime is going to be equal to the center to center column span. For beam span, you subtract 2 times SH, like what we have here in this equation. This can help you out figure out the mechanism shear. So to do the mechanism shear, you need to know how much is the probable moment at the hinge, and the probable moment at the hinge is going to be equal to, like this NPR, it's going to be equal to this factor, CPR, times RY. You have this from the table, the 1.1, times FY, in our case, it's going to be 50 KSI, times Z of the RBS itself. Z of the RBS itself is going to be a reduced value from the R for the beam itself. So the beam plastic modulus or section modulus, you're going to be taking it. Let's see here how this is ZE, which is the same as ZRBS. You're going to take in ZXB for the beam itself, as you read it off the tables, the steel manual. And then you apply this subtraction, right? You're going to be reducing it by this amount because the amount of cut that you do in the beam, top and bottom, right and left, which is the C amount. If I may go back, let's give you this piece here. So when you cut a section, you're going to see the beam section, and then you're going to have a cut in the flange, top and bottom, right and left of it. So we have this. Now we have the ZE or Z of the RBS. I would prefer to call Z of the RBS. And with that, you can figure out the probable moment. Now, how about here's the equation for the probable moment. Here's the CPR equation that you guys know how to find this out. You have F sub Y for the steel that we use. And then you have also F ultimate for the same steel. And you find out this CPR. After this, you do the mechanism shear, which is this VPR. You're going to be taking 2 moments divided by L prime, the clear spacing or the center to center of the hinge. Now it's going to be kind of confusing. Someone's going to say, where's the center to center? Because look at this. It says distance between RBS centers. Yeah, so this can be the RBS center. So sometimes when you say center to center, it's going to be center to center of what? Of the column or the hinge. Now the first one, L sub 0, is going to be from center line to center line of the column. The second one, L prime, is going to be from center of hinge to center of hinge. So this is going to be from center of hinge to center of hinge. Now you have the probable shear or the mechanism shear, if you like. It's just called here mechanism shear. What is the definition of mechanism shear? I'd like to hear from you guys. What's your understanding? What is this mechanism shear? Yes? Any takers? This is going to be a good chance to gain some points. Bring a piece of paper. What is the meaning of this mechanism shear?
Is it
the position at which the shear failure can be caused, or the weakest point in a beam?
Okay, I'm asking definition of this mechanism shear. What is a mechanism shear?
Is it the shear at the plastic hinge?
Yeah, this is true, but there is also can be any other shear value at the plastic hinge. But which shear is this? I mean, is this the shear due to dead load and live load, or shear due to what? Or shear due to seismic? Because you know what? When you take the seismic forces, you put in the moment frame and you run the analysis to draw the moment and shear diagrams, you're going to be also getting some shear there. So which one you're talking about? The one that you get from your analysis, seismic analysis, or the one you get from dead load and life load, or what?
Seismic.
I think it's the shear due to the structure, like how the beams and columns are joined,
So if I'm going to be taking this previous slide set, right, and then find out the shear diagram based on the seismic forces, is it the same as this mechanism shear? It's like from seismic? Because this moment diagram and the shear diagram that you get once you run the seismic forces on the moment frame, you can also call them seismic shear and seismic moment. Is it the same? But I'm just going to be taking it at center of the hinge? Yes or no?
Yeah.
No.
Okay, a person says yes, another person says no.
I vote yes.
I vote yes.
No, it is not. It is not. It has no relation to it at all. This seismic forces that we have been talking about, this is based on our seismic analysis, based on the mass of the building, based on the initial period of the building, based on all of this analysis that you are going to be doing, right? Based on this. And with this, you're going to be obtaining some seismic forces you put in the moment frame, and then you solve the moment frame, you get some moment and some shear, right? Like in here. This shear here is completely different. This shear is just based on the member size that I have picked and chosen. So I have chosen here, let's say W27 by 84, right? For the beam size. Based on this given beam size and based on the column to column span, based on my choice or the selection when it comes to A, B, and C, right? Now you start to push the moment frame all the way to the right with any given forces, and then you keep on adding force and adding force, you just increase the force. At a certain point, the moment frame is going to start to hinge. It's going to start to do something like this, right? And then after that, you push it, the force is not increasing, the force now stopped. But you have more deformation because, at certain point, right, we understand that we're going to have this elastic plastic or elastoplastic response. What does it mean by elastoplastic? Here is the force or the stress, and this give you the strain on the y-axis, right? And you guys are aware of this stress strain diagram. We have something like this, right? So what's going to happen here? You start to push the moment frame with some force. Let's say that you put 60 kips, 70 kips, 80 kips, 90 kips. All of a sudden, I'm just throwing here some numbers, right? All of a sudden, at this 90 kips, what's going to happen? The hinge is going to start to happen. And then after that, you're going to have lots of displacement and no increase in the force. So the force now is going to be constant, it's going to be maxed out. And at that point, you're going to see the hinge now is going to start to form. So this has nothing to do with the actual force that you're going to be designing for. The actual force that you design for is actually based on the amount of seismic force that you put to the one frame. But this force that you're talking about, it's going to be based on what? It's going to be based on the beam section, on the section, right? On the section itself. W27 by 84, this is like one of the beam section size that you can use. So based on the beam size that you assign here, you're going to be obtaining this type of force and this type of performance. Meaning, this is here is going to be like external force demand, and this force that you're talking about, this force that you're going to start to yield about, and this shear here is going to be based on the actual performance of the building. It is not really capacity. It's going to be based on the actual performance of the building. Once you start to push the building with some displacement, this is going to be the amount of shear that you're going to be able to develop in the beam. So it is not related at all to the moment and the shear distribution that you get from the given seismic forces. Does this make sense or no? I'm not clear yet.
Yeah, that makes sense.
Okay. So is there any relationship between the shear that you get here from the seismic force application to the moment frame and between this mechanism shear? I'm just repeating the question.
No.
So, okay, this mechanism shear is about the performance of the beams and the columns. As you start to push the moment frame, and at a certain point, you're going to be forming the hinges. And what's going to happen after this? the force, lateral force, not going to increase, but you're going to be developing some set of forces within the moment frame itself. We are really concerned about this mechanism shear, because if you look here at the moment, we said moment's going to stay constant, right? The moment here is going to be reaching a point which is corresponds to this amount of lateral force. You're going to be developing some moments, and this moment's not going to be going up. Our problem actually is going to be the shear, because this shear can damage the beam, right? So your choice and the selection about the beam size could be very critical here. So you want to be sure that you're not damaging the beam. Now, the total shear at the RBS, of course, you need to include the dead load and live load component. Now, how would you get this V dead load and V live load? You're going to say, well, let me look here at the mount frame. Let's say that you have a mount frame, right? And now you start find out this is going to be from center to center. Let's say here's one of the beams. I'm going to put this uniform load. So I'm going to put here uniform load on the top of the beam, let's say, right? Here's uniform load due to dead load. And then you find out the shear at the plastic hinge, which means at this location, right? The shear at this location due to dead load. Here and here, right? I'm going to say here's the hinge location. Here's the other hinge location. Because in each beam, you're going to have two locations for the hinges, right? So what you need to do is find out the amount of shear right at the hinge, right and left, right? This is going to be due to dead load and also due to live load. And this is going to be the two values that you're going to be using here in your analysis, right? It's going to be this V dead load and V live load. So this V dead load and V live load is going to be at the RPS, which means it's going to be at the plastic hinge, exactly at this location. And of course, you need to add to it the mechanism shear. So once you're going to be this V of the VPR is going to be additive. At one time, it's going to be subtractive. Why is that? Because look at the direction of the shear. At one time, this is going to be additive. At the other time, it's going to be subtractive from the other side. Now, which one would you like to consider when you do a check on shear? Yes, of course, this is going to be the additive one. This is the one I'm going to be using, right? Because you're going to have your higher shear because you have the dead load and live load components. It's okay. Now, I need to check the moment at the face of the column. Now, this check on the moment face of the column, it is not really about the design seismic forces that you started with. It's not about these forces that you have taken from the seismic analysis. Actually, this is still, we're talking about the performance of the moment frame itself. What's going to happen within the beam if we push it, or the moment frame if we push it to that limit, to that extent. So I'm going to say, based on this NPR, right? Where's the NPR? Which is this NPR, which based on the properties of the section that I used. It is not really related to the moment demand or the shear demand from the seismic forces, right? From the moment frame analysis. It's going to be based on the section itself. Based on this, and also based on this mechanism shear, I need to check and see if face of the column, which means the beam itself at face of the column, is okay. Which means I'm really, this analysis here, what I'm trying to do, I'm trying to check to see if the RBS that I picked, which means A, B, and C, is okay. I'd like to be sure that it's going to be safe when it comes to the beam itself. Because some people can come and take this plastic hinge and instead of putting it here, they're going to put it, let's say, close to the middle of the beam, for example. I asked you a question last time, and I mentioned for quick, I said, where would you like to put this plastic hinge? You want to put it closer to the center of the beam, or do you want to push him as much as you can? I guess the conclusion would say we'd like to set him further away from the center of the beam as much as possible. We'd like to get very close to the column. And what is the reason for this? The reason that we say that, we said when this distance becomes larger, this L prime, when you set them away from each other, the two hinges, your mechanism shear is getting reduced. And why is that? Look at this equation. When this L prime goes up, V PR, which is mechanism shear, is going to drop down. Another thing also is going to happen. This cantilever length, because if this give you the hinge, right, this give you like, it's going to perform like a cantilever. So in reality, it is not really a cantilever. And look at it. I mean, it's connected to the beam, but it's going to be acting as a cantilever because this give you like a hinge, right? If I'm going to go here to this, to the picture, I'm going to say, this give me the cantilever I'm talking about. You see this piece, this length? I'm just call it is gonna be acting as a cantilever, but it is not a real cantilever. So I'm gonna say here, once you start to push the plastic hinge location towards the column, close to the column as much as possible, this cantilever length is gonna get reduced. And this is gonna help me out for the moment at the face of the column. This moment here is not on the column. This moment is gonna be at the beam, right? This moment is gonna be at the beam, right? At the face of the column. It's gonna be equal to MPR. So MPR is not gonna change, right? Based on the location. So whether you put the hinge right here or the RBS cut, I'm gonna put here a circle, I'm gonna say whether you put it here or you move to the right, MPR is gonna be the same because MPR is gonna be about the selection of your B and C, right? It's not really about A. A will dedicate the location, and B also is going to be dedicating from here to there, right? But mostly it's going to be A, and partial is going to be B. So this MPR is not going to get changed. What's going to get changed is SH, right? Because look at this SH. SH is going to be the location of what? Of the hinge, center of the hinge to the face of the column. So if you start to push it towards the column, this is going to be good, right? As much as possible. Why? Because this is going to help you out to reduce this component of the moment at the face of the column. But once you start to push this hinge right in here, what happens to SH? SH is going to be grown up, and the moment at the face of the column is going to be higher. And here's the check. Here's the first check that you need to do, right? When you come to analysis, you need to check that the gravity moment, right, which is W squared over 2, like this is going to be the one that we use for a cantilever. Here's the cantilever. Or the section of the beam is going to be acting very similar to a cantilever, right? That's why the equation is going to be like the same for cantilever. Is going to be equal to roughly maybe 1% or 0.5% of this total moment at the face of the column. And also the other check that you need to do, if you look here, this is going to be the real check that you need to do, come to capacity, that you want to be sure that the moment at the face of the column, which I call here demand, is going to be lower than this capacity. So I'm going to say this is going to be pays here, this is going to be demand, and this is going to be the capacity. So we want to be sure that this is going to be smaller than this. And the equation says it needs to be less than 1.0, meaning that this value here, this capacity is going to be greater than this. The capacity here, when you use the phi here is going to be equal to 1.0, right? And MPE is going to be based on R sub Y only. CPR is not going to be included there, right? So you'd like to reduce MF as much as possible. And the way to reduce MF, as you know, is to bring this as close as possible to the left, right? By reducing A. So you try to make this A as small as possible. This is what you need to do in your design, if you like to control your design. Any questions so far? Or all the way up to this point? All right, seems that you're good. Now, how about the shear strength? Now I'd like to back check the shear. You can say, okay, so at this point, I checked the moment at the face of the column, moment in the beam. So now I confirm that my selection of A, B, and C for the plastic hinge, for the RBS cut is good. Now, how to check the shear? Now we need to find out the shear demand. Shear demand, again, is going to be equal to, this is going to be what? Mechanism shear plus V gravity. This is going to be V RBS. It just says here V gravity, but someone here need to think carefully about this and say, it's not just V gravity, you need to follow this load combination. So V gravity, actually, the way it's mentioned there, in this equation is going to be this section. I'm going to call this going to be V gravity in the ultimate level. And this is going to be mechanism shear. So, okay. What do you do after this? Now we need to check the shear. How do you do this? You say, when? I mean, I guess you guys are familiar with this. In your selection to the beam, right, you need to be sure that dB divided by the web thickness, right, T of web. This is going to be the depth of the beam. It's going to be within this value. It's going to be kind of the compactness when it comes to the shear. You don't want the web to be very thin, and if it becomes very thin, you're going to have much less shear capacity, and buckling of the web in the vertical direction may happen. So what you need to do, you need to be sure that your beam, right, your beam depth to web thickness is going to be within this value here. It's going to be lower than this value. So you'd like to have here a thicker web. You don't go with a very thin web when it comes to the beam. And here's the check. This will give you one of the checks. Now, Vn is going to be equal to 0.6, which we have done before, times Fy times area of the web times CV, and CV is going to be equal to 1. So this is going to be exactly what we have done before. Now, what phi factor should we use? This is going to be the question, right? So I'm going to say, okay, this one we need to think about. What do you think? What phi factor should I use here? Should I use 1 or should I use 0.9 or what should I do?
I think 7.75.
Here is what we have done before. We come to the shear check. We have done it here, right? Did we? Yeah. What phi factor do you use for the shear?
1.
Oh, so where did you get the 0.75 from? Concrete design? It's concrete design, right?
It's for shear rupture.
Yeah, this is for concrete design, but look at this. Piece of V for the shear is going to be equal to 1.0 and CV is going to be equal to 1. This is for steel, but when it comes to the yield strength, we don't really use it. But instead, we're going to be using how much now? 0.6, which is very standard. And here's the equation for the shear, right? 0.6 times Fy. This is usually standard when it comes to any shear. So I'm going to say, okay, look at this compactness, check. H over TW, it's going to be within 2.24. How about here? 2.45. Which one to use? 2.24 or 2.45? Let's say for gravity beams, I'm going to be using this. For moment frames, I'm going to be using this. But the same concept, there's a check. There's something there to limit the depth to the web thickness. This is going to be the bottom line. Now, H in this case is going to be the same as dB, the same as depth of the beam. Here we call it H, here we call it dB, it's the same, all right? So again, what phi factor should you use in here? It's going to be 1.0. And we'll see more. Now, after this, we're going to be doing something that we call here continuity plate. What's a continuity plate? Anyone recalls? Here's a continuity plate, this plate. We have it on the top, we have it also at the bottom. I just want to check here for quick. Okay. This is going to be the continuity plate. You see this plate? This is a small plate. You have top, both sides of the column. You have also at the bottom, both sides of the column. So why are you trying to put here this continuity plate? I'm going to say because if I'm going to put here any tension force, right? This tension force is going to be going throughout the width of the beam and again get transferred to the column flange. Like in plan view, if you like to see it, I'm going to go back here, right? I'm going to be looking at this continuity plate, meaning that you're going to be putting here some stresses. It's going to be coming this way, right? Like some tension force is going to be distributed because it's going to be coming from the beam flange to the column flange, right? Now, if this flange is going to start to be pulled this way, I'm expecting that maybe the flange is going to be doing this, right? It's going to be bent this direction. And from this side, it's going to be also bent this direction, which is not good, right? So I'm going to see some trouble here. So the best way, right, instead of putting bending on this flange, now I'd like to bring this force all the way to the web, right? So the conclusion, if you have any shear or any tension, I'm going to go back here and say, if you put here any tension, you'd like to transfer it to the web of the column. So you'd like to engage this flange and bring the entire force to the web of the column. So let me go back here. How do you bring this to the web of the column? If you start to bend this beam, for this column flange, you're going to be hurting the column flange here, right? You're going to be reducing the strength of it. And you're going to start to dissipate energy in this location, which we don't want to. We want all the energy dissipation to happen here. So how do you here enforce the integrity for this connection? So you need to put plates, one plate here, one plate there. So the tension force is going to get transferred from the beam flange through the column flange to the continuity plate without bending the column. Because look at this plate here. This plate is going to be like a very strong stiffener. It's going to be welded on three sides. It's going to be welded here, right? See this welding? It's going to be also welded to the column web, and also it's going to be welded to the column flange from this side. So with that, all the force is going to get transferred. So some of it is going to get directly to the web, some of it is going to be going to the column flange, then the continuity plate, and then it's going to get transferred through this weld here to the column web. So I said, okay. How would you know that you need it? You really need to put this continuity plate, or you can just ignore it? Because I'm going to say, when do you think you're going to ignore it? I'd say you can ignore it if this column flange is so thick compared to the tension force that you're talking about. So if this is going to be very thick compared to this force, this means that this rotation and this kind of bending on the flange may not happen at all. It depends, of course, on the column section and the beam section. You say, okay, so I need to do a check here, and here's a check. Check says TCF. What is T? Usually, TF is what? Can someone help me? Flange thickness
Of flange.
of the column, right? Flange thickness of the column. Oh, is it about the flange thickness of the column? I'm going to say yes. This continuity plate, someone may think and say it's really about the beam and how much force you put from here. I'm going to say it is also about this section of the column, right? Because we say bending and not bending and this kind of things. So I'm going to say the flange thickness of the column, if it is more than this value, and this value pays on what? Pays on properties from the beam. Look at these values here, Fy of the beam, Ry of the beam, divided by Fy of the column, divided by Ry of the column. So it's about the beam and column properties, right? Look at this. It's going to be for the beam, beam, column, column. It's about the properties, right, of the frame beam to the frame column, right? And once you do this check, right, and you have a very thick column flange, in this case, you don't really need to have continuity plate. So this is too big, right? This is why when you look at this, it says continuity plate not need to be provided. And this makes sense. Yeah, this goes here with our discussion. We said if the column flange is too thick, right, which means it goes beyond this requirement, you don't really need to have continuity plate. You don't need it here. But if not, you need to have it. And also it says when the column, so you have here two conditions that you can provide either one of them. It says here TCF, which means the column flange is going to be greater or equal to the width of the beam flange divided by 6. All right. So I'm going to say here, this is good. So what happened if I need it? So I said, if I need it, now we have here some issues that we need to provide. Oh, excuse me for a second. So now you decide that you'd like to have this continuity plate, right? So here's a continuity plate. It is needed because here's what happened. The flange thickness of the column is going to be less than this value, right? So I need to put one gen that you don't want to work through it. So this actually, this K for the column or K1, you're going to see it in the table. But in your submittal, you're not going to go there because in your submittal, you're going to stop right before this. And this is what I wanted from you. It's just to design this, to do this design. You do check on the shear and check on the mount for this size mold frame. This is why I'm switching gears here to submit to slide set number 12. Slide set number 12 is going to be a solved example. So I want you to have an access to it, right? During your time off so that you're going to be able to do your submittal for the mount frame. So continuity plate is not going to be included in your submittal. In this example, it shows here governing code. It says 2006. This is going to be the problem, the solved problem that we have and we're going to be using. So whether you have it as 2006 or you have it as 2018, it's going to be the same because what I care about is going to be the amount of words that you're going to be using. So based on the given code, you have this importance factor. Right? So let's say for us, it's going to be 1 equal to 0. So we don't really care about the details of this. And SS and S1 and this kind of things. What we care about is going to be the sizing forces that you're going to be assigned to your mold frame. You have also building description. It's going to be 8 bay by 8 bay, center to center span. You have lots of information about the building itself, which I don't really care about for now. What I care about is to find out at the end, at certain point, you're gonna figure out the amount of loads that goes to the beam, like in terms of gravity. And once you do this load combination. So this give you the load combination that I put in the red box that you need to use W ultimate. It's gonna be equal to 1.2 W dead load plus 0.5 W life load. Please don't use 1.2 plus 1.6. You don't really need to do this. This give you the load combination that you use once you have also the size gonna be get added to it. So this is gonna be V gravity, right? So V gravity is gonna be equal to 1.2 plus 0.5. Now you need to figure out the loads, right? In here, it was figured out to be 28 kips, and this is gonna be right at the center of the RBS. So in your case, you need to figure it out. At the end, you have this load combination that you need to use, and then you can figure out the amount of load that comes to your moment frame beam. How do you figure out this W? Like a uniform load, you're gonna have the load goes to the column directly or goes to the beam and then goes from the beam to the column, and you can figure out this uniform load for this case, for your case, in your example or homework. The beam size that was used in this example, it's given here W36 by 282, is very heavy, extremely heavy. You're not gonna see a size like this in our project. And give you here, the steel is gonna be A992. Fy for the beam is gonna be 50 KSI, and same thing for the column is gonna be 36 by 395. Give you the same F sub Y for the column is gonna be 50 KSI. So the material property is gonna be very similar to what we use in our project, but the beam size is gonna be different. So okay. Section properties for the beam and for the column. Would you get all of this information? Let's say you just open the steel manual. In the steel manual, you have this beam section and this column section, and then you can bring all of this information, you just put it there. This is gonna be an easy step, right? Because I'm gonna give you here the column size and the beam size. So you can look up all of these values and write it in your Excel file, or maybe in your Word file, or if you're doing handwriting, it's gonna be up to you, the way that you do it. Information includes the depth of the beam, width, flange thickness, web thickness, ZXP, and this ZXP is gonna be for the beam itself before you apply the RBS reduction to it. And of course, this is gonna be radius for gyration, you need to have it, and the moment of inertia for the beam. Same thing also for the column, but for the column, you need the cross section area because you're gonna have an axial load, and then you need this value there. So okay, number 2, I need to come up with what? The A, B, and C. For the RBS, for the RBS choice itself, I need to have A, B, and C. If you go back here to our slide set, not this one, slide set number 11, which is this one here, I have a range for A, B, and C. So look at the first range. First range, it says for the A location is gonna be somewhere between half of this number, which means it ranges from 8.3 to 12.5. Look at the choice. We're gonna go here with 8 inches. So try to avoid half an inch. So someone can say, well, can I use 9.5? I'm gonna say yes, but why would you put numbers like this? Just use simple and easy numbers for you. So pick 10 inches here, like what happened. So this should be fine because you went between the two limits, right? For the upper limit and the lower limit. Now, do you think it's better to go to 12 inches or it's good to go to 9 inches? Which value would you pick? If I have here a choice, I'm gonna say, would you go to 9 inch or 12 inches? What's gonna be your choice?
9 inches.
9.
I'm gonna go to 9 inches. I'd like to reduce A as much as possible, get the two plastic hinges away from each other, reuse the plastic, I'm gonna say the plastic shear or the mechanism shear, if you like to call it this way, the VPR. Gonna look also at the range when it comes to B. Look at B value. It says B is gonna have two values here. Here's the range, 65% to 85% of the beam depth. So I have it between 24.1 to 31.5. I decide here to go with 28. Yeah, this makes sense. I mean, the length of the plastic hinge is not really critical, right? The plastic hinge itself, the length of it, which is B, because look what happened. If you change the length and make it shorter, what's gonna happen? If you make it longer, what's gonna happen? If you make it here longer, you are pushing this plastic hinge to the right, which is not good. If you make it very short, you're gonna have lots of damage. This is gonna be now based on performance, not analysis, right? Based on previous observations, if this is gonna get very short, you're gonna be damaging this area here a lot during an earthquake. So you'd like to have a real value. I'm gonna say maybe in the middle, 28 inches sounds good to me. So I'm not gonna go here to 24 inch to make it small and push the plastic hinge to the left, right? So I'm gonna make it real some value in the middle. It's gonna be good. All right, now also you need to look at C, the C value. I'm gonna have here a range also for the C value. Here it is. It's gonna go from quarter of B of the beam flange to 10%. So I'm gonna go here. Here's gonna be the C. I'm gonna have here a range, and once I'm gonna be within the range, it's gonna be good. They have a target here, and their target is to have a reduction of 45%, reduction in flange area. That was the target. Now, where is this coming from? You don't want to really go beyond 45%. You'd like to keep it, let's say, roughly about 45%. So as I said here, if you reduce it 45%, now take this 45% and then take, let me put this back, the flange thickness. If I'm going to be looking at this, here's the width of the beam. Take half of it. You see, here's half of it, right? And then take 45% of this length. It's going to give you here the C value. It's going to be 374. So you're going to be very close from 45%. So you're going to go here to 375, right? 3.75 inches. Here's going to be the cut, which is going to be okay. It's going to be within this range because look at this range. Now just look here at the range. The range, it goes from 10% to 25%. 25% means what? Of this B means 50%. So this here is going to be going to 50% of reduction in the flange width. It's going to be 50% because it's going to be quarter of the entire flange thickness. And here is going to be how much when you go here 10%? Can someone help me with this?
20%.
20% reduction, right? Which means 80% effective. It's going to be 20% reduction, right? So you'd like to keep it close to B, close to this value, but you don't want to go beyond this value. So you say if I'm going here to 3.75, how much this is going to be? Now divide this by 16.6 is going to be 22, which means that you're going to be at 44%, right? So I said fine. It's going to be 44%, close to this. Sounds good to me. Now we can figure out the radius. What radius? I'm going to say radius based on this equation. The radius for this of the circle here for the cut. This can be only for fabrication. You don't need it anymore for the analysis, right? And of course, you'd like to get a good number. So in reality, what's going to happen, let's say that your answer is 27.5. You need really to have a good number for the steel fabricator. You're going to make it here 28 inches. Just you guys know. Now you're done with this. Now you have the radius. Now we have the RBS choice. Now I guess this says here recall, which means this is taken from previous slide set. This is taken from here, right? Right? Nothing is new here. It's going to be the same slide. Now you need to figure out S sub H is going to be based on the column properties and the beam properties that you have. So it's going to be based on the column. It's going to be the column depth, and then you have A, B, and C that you have just picked up, that you went up with in here in this analysis. And after this, you need to find out the center to center of the plastic hinge. So it's going to be from plastic hinge to plastic hinge. It's going to be L prime based on this equation. Once you do this, here's S sub H, 43 inches. L prime becomes 20.8 feet. Now also you need to figure out the reduced beam section modulus. Now how do you do this? You take ZXB. Where do you get this ZXB? You can say 1190. It's going to be from the beam choice, and the values that you look up in the steel manual, it's going to be right here, 1190, right? You take this, you start to reduce it for the plastic hinge. So it's going to be minus C, and then you have all of these values from the beam section itself. Now with that, you have the reduced section plastic modulus. And also you can do the CPR and look at the CPR value. Yield strength is going to be 50. Ultimate strength here according to what you see, is going to be 65 based on this material. You divide by 2 times f sub y. Now I have 1.15 is going to be less than or equal to 1.2. Now my question, if you have given steel and it turned to be 1.25, what value would you use? Would you change the steel or just use 1.2? So we're going to say in this case, you're going to cap it to 1.2, which means just use 1.2, don't change the steel. You're going to be using it. MPR, which means the probable moment. Let's give you the probable moment at the RBS itself. It's kind of the maximum moment that you can develop at the RBS itself, not in the beam. It's going to be at the RBS, the reduced section of the beam. So you're going to be taking CPR, the 1.15. It's going to be taken from here, right? 1.1, where'd you get this value? Anyone recalls? What is the source of this? Anyone recalls the value? Where it's coming from?
The table for
RY value?
341.
Slide
It's a
set
table.
10. Is it slide set 10? Slide set 10, right? Here it is. 192, it's going to be 1.1. It's going to be this value. And R sub t is going to be 1.1. You say here's this coming from the table. This table here, 3.1 times f sub y, the 50 times 772. What is the 772 again? I say this 772, this value here. ZE for the RPS itself. So I'm expecting here to have a moment, right? Once I push this moment frame, I'm gonna have a moment value of this much at the RBS itself. Now, where is the mechanism shear? You can call this to be the mechanism moment. This gives you the moment at which the mechanism is gonna happen. What is the mechanism? Can someone tell me what is the mechanism in your opinion? What is the mechanism?
Is it the critical value for a moment in this case?
What do you mean critical value? What does mean by critical value for you?
That the system or the structure will start to, let's say, bend.
Bend? At any value, it's gonna start to bend.
No, but like as in a plastic behavior. Yeah, like this.
Okay, yeah, once it's gonna be going into the plastic response or behavior, this is what we're gonna be calling it to be the mechanism. So mechanism happens when this shape that you're looking at is gonna happen, and once the plastic hinge is gonna start to form. We call this the mechanism. So I'm gonna say, this is gonna be the mechanism moment, and if you take 2 MPRs, according to this, divided by the span L prime, which is the center to hinge to center of the hinge, this can be the mechanism shear, right? So see, here's the mechanism shear, 2 times the probable moment, which means the mechanism moment at the center of the hinge, divided by L prime. L prime is equal to how much? 20.8. What is this 12 for? So I'm gonna say this is gonna be what? L prime, right? I'm gonna put it here, this is gonna be L prime. Can someone help me with this 12?
It's conversion from foot to inch.
Conversion, right? Conversion factor, right? Because this MPR, the 48,829 watt units, it's gonna be kip inch, and this is gonna be in feet, right? This length here is gonna be in feet, so I'd like to convert it into kips. So this also needs to be in feet. So now I have 391 kips. It's good. Now I know this value here. I know the amount of shear developed if you push this moment frame. This has nothing to do. Now let me go back in the same slide set. It has nothing to do with all of this analysis, right? With the seismic forces that you're going to be calculating out on the moment frame. This is based on the choice, on your selection. Now someone's going to say, now where's the design? What did we do with the seismic forces and the moment diagram and the shear diagram? I'm going to say it's going to be coming, but not now. Okay. Now I have the mechanism shear, right? This gives you one thing that I want you to do. And then after that, after you have here the mechanism shear, you need to find out the shear at the RBS. How do you do this? You say the gravity, right? The gravity was 28 kips. You take the gravity shear, you start to add it to the mechanism shear, the 391 kips. Here we go. And then you subtract it once. Now, which shear do you think is going to be controlling your design?
Higher value.
Say, yeah, the higher value. It says here, control the design. It's that simple. I said, okay, now I'm going to have a maximum shear of 419 kips. And this is one thing that I want to be sure that the beam is going to be able to take this, because this mechanism shear and this total shear that you have at the hinge is based on what? It is based on the mechanism moment, right? But we are not sure if this beam is going to be able to resist shear or not. But we know that this shear is going to get developed because based on this mechanism moment and based on the reduced section, we're able to come up with some mechanism moment. It's going to be the moment at which our beam or our moment frame is going to start to go through the inelastic response, right? So for this moment here and for this displacement, I want to be sure that the beam is going to be okay to take the shear. So what do? I find out mechanism shear, then total shear at the RBS to include a little bit from the gravity load with this load combination. Now at a certain point, we need to check the shear, and here's the check of the shear, right? It's going to be coming here at this section, right? So I'm going to be, let's just skip it for now. Skip the few slides in the back here for the flexure check. I'm going to say V sub U is going to be equal to the mechanism shear. Just repeating the same equation again. Plus V gravity is going to be the 419. Now this slide number 15, I'm going to come back to it in a second. I'm going to say this is going to be the same as this 419, right? So this is the one that we say control the design. I'm going to say here, let's check the shear, right? 419. This dB divided by the thickness is going to be 41.9. Is going to be less than this value. The 59, it means that I have compactness when it comes to the shear check. Vn, which is the shear capacity here, is going to be 60% of Fy times area of the web times C sub V is going to be 985 kips with CV of 1.0. Look at this one here, 419 versus 985. This is great. We have enough shear strength, right? So I see this is good. So I don't have here a problem with the shear strength of the beam, right? The problem is going to happen if you're going to be picking here a very small whip beam. If you like, the thickness of the whip is going to be small. And all of a sudden you do this check here, and then you find out that your beam is unable to take this shear at that location. So in this case, you cannot really continue. You need to go back and change your beam size because you'd like here to have enough whip thickness to be able to take this amount of shear, right? So the problem is going to happen if the beam flange is very thick, this MPR is going to be high, and this shear demand is going to be high, right? Now, all of a sudden, you back check it versus the shear strength of the beam itself, and you find that it's not working. Or another problem is going to happen if you have a good beam size for a moment frame, and then you go here with a very small center to center of hinge distance, which means this L prime is going to be very small. Now, all of a sudden, the shear demand is growing up, is going to be real high value, and then you do a check in the shear, it's not working. So in this case, you may want it to play first with L prime and reduce A as much as possible before you start to change the beam size. But if you really have to change the beam size because you set A to be the smallest value as possible, right? So in this case, you need maybe this beam size is not good for the shear, and you need just to change it. You need to pick another beam size with maybe a smaller flange and maybe thicker web. Maybe this gives you the direction. So now we're done with the slide 15. I'm going to go back here to check the moment at the face of the column. This is also repeated slide. It is taken from here. If you may recall, this give you the one for the check at the face, right? This give you the check at the face of the column. So we're going to say here the moment at the face of the column is going to be equal to MPR, the mechanism moment, or the probable moment at the hinge, plus this the V at the RBS. You consider this to be a cantilever again. This is the one that I was just talking about, right? Times SH. Now, SH definition is going to be different. In the past, SH used to be to the center of the column. In this analysis, it needs to be to the face of the column, as this distance here. So you take the V at the RBS, and as you see here, this is treated to be like a cantilever system, as if it's going to be a cantilever, because in this case, you put the vertical load is going to be right here in the middle, and you just take this force times this distance, which means as if this is not here. True is going to be continuous, but because of the plastic hinge, this is going to be treated to be like a cantilever system, right? So you just take this load times the distance SH to the face of the column, again, say this distance. Let's give you the moment at the face of the column. This is here treated to be like a moment demand. but it's the moment demand based on the amount of displacement. It's going to be based on the mechanism. This is not going to be the moment demand that you get from the seismic analysis. So I'm going to say, what do you mean by seismic analysis? I'm going to say from this, not this one. And say from this, based on the seismic forces. You know the one based on the seismic forces? Like this seismic forces that we were talking about, right? The seismic forces and about the moment frame analysis that we have done to obtain this moment diagram. You know, no, this is not about that. This moment here at the face, it is not this moment at the face. This moment at the face, right? This M max, this is based on the seismic forces applied to the moment frame. But this moment at the face is going to be based on the mechanism, which means you want to be sure if this is going to be going through the mechanism, right? Which means it's going to be going into the inelastic analysis, that this beam section right here is going to be staying in good shape. Because if this is not true, if this moment at the face is lower than the capacity of the beam, it means the hinge is going to be forming here, right? So we want to be sure that we are controlling the hinge location. So all what we are doing here, we are trying to control the hinge location is going to be here. So how do we do this? We'll be sure that this is going to be hinging first before this location. Because if this is going to be hinging and this is going to be hinging at the same time, it means the plastic hinge is going to be right here. It's going to be like this, right? So we'd like the plastic hinge to be controlled only in this location. Do you remember what was the problem here? Would the hinge to be extended to this location? Can someone help me with this?
If the hinge is extended to the face of the column, that means it will be weaker at the face of the column, and we don't want that, right? We want
This is going to happen. So you're going to have cranks here in the weld. And this is actually a very good question. Let's say for one of the exams, right? I can ask here that I was doing some analysis, and then all of a sudden, this moment at the face of the column based on this analysis turned to be lower than the capacity. What capacity? I'm going to say this give you the capacity, right? The capacity of the beam itself. So what does it mean for you? What is the expected damage? You can say expected damage give you something like this. It's going to be crack, right? You're going to have here crack in the weld. Why? Because you push the plastic hinge to happen at the face of the column. Make sense? I guess from time to time, I give you here parts and pieces of the exam. I hope that you guys are taking some notes, I would say, that you're listening to me. So if everything is good, it means that I kept the plastic hinge in this location. If this condition is not met, what condition? I'm going to say this condition here, right? If this is going to be more than one, if this demand here is greater than this capacity, it means that the plastic hinge may happen here, which is bad, right? You should expect cracks at the weld between the top flange and the bottom flange to the column. This here a picture of the bottom flange. So I'm going to say here top and bottom flange. Here, you're going to have a damage here and there in this welding, right? So you don't want this to happen. Here's moment at the face of the column, but this is going to be in the beam itself. It's going to be equal to MPR. This is going to be the mechanism moment, which happens right at the center of the plastic hinge, plus V of the RBS times SH. Here's a V of the RBS, 941. And then it says here, times 10 plus 28 over 2. So I'd like to figure out what is this 10 inches. Anyone recall the 10 inch? Where does this come from? Yes? It's going to be A distance, right? A, right? What is 28?
B.
28 is going to be B. This is correct. So actually this SH, this going to be SH. If you remember, this going to be SH. But which one? Which SH? So I'm going to go here, right? No, not in here. I'm going to say to set number 11. I'm going to say which SH is going to be this SH. So this here equals to B over 2 plus A, right? Here's A, and from here to there, it's going to be B over 2. Say, okay, 28 and 10. Let me go back and check. Just to be sure that you're not doing here a mistake, right? So I'm going to say, here's the choice. B is equal to 28 inches. How about A? We went with 10 inches. So I said, okay. This is very good, right? So now I guess we're following up with this. We say, here is the moment at the face of the column. It's gonna be this much. There's another value here based on the fact when you go to the other side of the beam, and then you're gonna have a negative shear. The shear is gonna be much lower. Then you can do also this equation, because on the other side, at one side, the shear is gonna be additive, at the other side, the shear is gonna be subtracted, but the moment also is gonna be negative. So you try both of these two values, and usually this positive sense is gonna be control your answers. But this is also a check that you need to do. Okay. Now this give me the face, the moment at the face of the column and the beam itself. We're gonna be using this. How about for the gravity moment? I'm gonna say yes, because this also works as a cantilever, right? So for the cantilever, I have taken all the gravity loads coming from this side, and also the mechanism shear I put as unit load, like a point load. But also I have some gravity loading here, right? I have some gravity load. W ultimate is gonna be right here. So let me put it right there. Again, here your W ultimate that you just calculated is gonna be acting right here. And this looks like a cantilever in performance or behavior. So I need to take this W ultimate times this SH, right? Which is the same value here, squared divided by 2. So it's right here. Look at this. W ultimate, SH, 10 plus 28 divided by 2 squared. And of course, divide by 12, because I have this here to be in inches, I need to convert it into feet. This is gonna be here kip per foot, right? 2 kip per foot, inch, divide by this to have it in feet, and here's the moment. It's gonna be 48 kip inch. So it's true that you divide here by inch, but at the end they put it to be kip inch. They convert it to kip inch. So okay. Now I need to take this value here and add it to my moment. I just want to be sure that according to this, that this moment here can be ignored. So if it's gonna be less than 0.5%, you can ignore it. But if you like to take this value here and add it to the 58.85, this is gonna be okay. So in some cases, you can just ignore it because it's gonna be very small, or you can just add it to this value. So what happened? It was just ignored in this case because you use 58.85, right? But if you like to do a spreadsheet, just add this value to this value. Just add on top of it. So okay, good. Now MPE, which is the capacity now of the beam itself at the face of the column, is going to be equal to, if you remember that CPR is not going to be included, which is kind of tough when it comes to the code here that they reduce. That don't forget that M at the face, the CPR was included there. The 1.15, right, was included in the denomination of this M sub F. But when it comes to capacity, you don't include it. Someone's going to say it is unfair, but we're going to say, you know what? Yeah, it is unfair. But I mean, we're not writing the code here. We're just following the code. ZBX, this is going to be for the beam itself, the 1190, 1.1 is going to be the R sub Y times 50. This is going to be the capacity of the beam. And of course, phi factor is going to be equal to 1. So capacity is going to be 65, and the demand is going to be 58. So it's going to be less than 1, which means your choice here for the beam size was good. Any questions for this analysis? You're going to stop here in your submittal. So don't forget, it's going to be sheet number or slide number 14 for the slide set number 12. I just finished some time. 6:43 now. Someone's going to say the same question again, right? What did we do the seismic forces? You have some seismic forces that you're calculating out, and you want to be sure that whatever seismic forces that you picked was okay. I mean, we don't want to be in trouble. Otherwise, why we do the seismic forces? Why do we care about the mass of the building? Why don't I just put any moment frame in any location with any size, gonna be working fine? You can say, the part that I didn't show here for you, and at one point we're gonna be working on it, is that when it comes to the moment diagram, right? So I'm gonna be putting here, let's say the previous moment diagram that we discussed, right? Let's say here's a moment diagram on the beam. What you really care about, let's say this is gonna be the, no, I don't wanna show it here. So I'm gonna be copying this from here. I'm gonna put it right here at the plastic end, right? It's gonna be like this. So this is actually what you're gonna be reading off your moment diagram when you do the seismic analysis. and this give you the moment value, this moment ordinate that you're going to be reading, and you call this give you the moment at the center of the column. So once you're on, let's say, a set model, right? This give you M ultimate at the column that you're going to be reading. I'm going to say here M ultimate at the column, which is this value here. This value, in reality, you don't really need it. I mean, you don't really need this value here. This give you based on the seismic force. Can you just show it here? But you don't really need to use it in analysis because it can be taken by the column. Also, you don't need the moment here in the face of the column. What you need to work with is going to be this moment. I'm going to say here at the RBS. This is going to be M ultimate at the RBS. Right? Give you from seismic moment frame analysis that you do. Now, which moment are we talking about? I'm going to say this is going to be this moment from here to there at this section. So we're get again this M sub U for the RBS. Again, you're going to be taking this value from your seismic analysis when you put the seismic forces on the moment frame, and then you do your analysis with a SAP model, let's say. You're going to be doing here SAP 2000 or any other software. You just read this value here. Now, you need to compare this value with the capacity of the plastic hinge. So you want to be sure that the capacity of the plastic hinge, right, at this location is going to be harder than this value, but not a lot. You like to leave a gap, maybe 5% to 10% max. And this is how you're going to be picking and choosing the beam size, and then after that, the column size. So the choice of the beam size here, there's a step that we're missing, but you don't have to worry about it because I'll pick the beam size myself for you. Okay? Someone's going to say, how about the moment at the face? I'm going to say this moment at the face in reality will never happen. The only moment that may happen in analysis can be this moment here at the center of the RBS. This moment at the RBS is going to be the only moment that may be able to develop in the entire moment frame system. All right, any questions?
No, I think we're all good.
Great, okay.
I have a general question about the continuity plate, but I can ask after class.
No, it's fine, go ahead.
I was just
If anyone would like to leave, please go ahead and sign out. If you like to stay, go ahead and stay. Yes.
So I was just wondering, we put the continuity plates so that the flange of the column doesn't bend.
Yeah.
That's due to tension in the beam.
Tension or compression, yes, but tension, yes, mainly tension.
Okay, this tension or compression is usually in the beam flanges only, or the beam flanges in the beam web?
Most of the force usually, let's say that you have a beam, right? And you have a web. So you know the section, let's say this is going to be a section in a steel section, right? Steel section is going to be composed of two flanges and a web, right?
Yes.
So when it comes to the shear strength, we say it's going to be resisted by the web, correct?
Yes.
How about the flanges?
They don't resist much shear.
Actually, they resist some because they're exposed to some shear force, right? So they're still exposed to some shear force, but usually we say that this is going to be like based on analysis, right? When you look at the actual distribution of the force, you're going to see that most of the shear, maybe 99%, is going to be taken by the web, or maybe 95%. And a slight amount is going to be taken by the flange. So you say, now this is going to be a good reason for us to ignore the flanges when it comes to the shear and let's just take them by the web. So, okay. How about the tension force at the moment? We're going to say most likely it's going to be taken by the flanges. This is why when it comes to some analysis, I'm sure that you hear the term here, TNC, the couple, right? Here is going to be, let's say, tension, and this is going to be compression. Did you hear about this before? Usually we say. So you can just find out the moment, and you say moment is going to be equal to tension compression multiplied by the distance from the two flanges, right? So this distance here, you take this distance, apply by one of these two forces, going to get you the moment developed in the section. So generally speaking, we say that flanges is going to be responsible for resisting the moment, and the web is going to be responsible for resisting the shear. So now go back to your question. Now let's go back to it, right? So you said, where is the moment is going to be coming from? The moment is going to be coming the flange, like in here. Most of the moments is going to be coming through the flange. How about the web? Would the web see some of the moment, right? I'm going to say, yeah. But you know what? Look at the stress distribution, right? Let's say before it plasticized, it's going to be like this, right? So most of the flexion is going to be going through the flange, and also the cross-section area of the flange is going to be larger than that for the web. So we consider all of the force to be taken from here through this one here, right? And a little bit of a force is going to be going through the web. And if you have any force going to be going through the web, let's say that some of the tension force is going to be going through the web. So I'm going to put the web here. Here's the tension in the web only, right? So where's it going to go? It's going to go also to the web of the beam of the column. It's not going to be going to the flange of the column, right?
So
But-
in the you said it's going through the web.
Let's say that some force is going to be going through the web. I'm just saying some force is going to be going through the web. So in the depth here, some tension force is going to be coming this way, right? And a little bit of a tension force is going to be coming here. So I'm going to make it small, correct?
Okay.
So this force now it is in the web. How about in plan view? Where is it going to be at? It's going to be right here.
Yes.
So it doesn't really go to the flange here. It doesn't pull this piece out, correct? It just get transferred to the column flange, right, to the column web right away.
Yes.
Okay. So if you have any tension force in the web, it's going to get transferred to the column web directly. But most of the force, you're going to see it in the flange. This is what's going to happen in flexure. In flexure, most of the force is going to be taken by the flange. You remember in concrete design, you put the section, and then where you put the steel, you say all the tension is going to be here. About compression, you say compression is going to be here. And do you remember this little bit of a section area? It's called A, right?
Yes.
Now, where's the tension compression? You're going to say it's going to be in the extremes. How about in the middle? Do you have some transfer for any tension compression? You're going to say, yeah, a little bit, but not much. Same thing here. The web, generally speaking, is going to be very small. It doesn't take lots of moment, if you like.
Yes. And then these tension forces are caused by seismic mainly.
It is no, it's going to be gravity and seismic. But when you look here at the gravity loads compared to the seismic loads is going to be much, much larger, to a point that you can ignore the gravity loads.
Okay. Yeah. So mainly the tension in the beam is caused by the seismic loads.
Yeah. Here's an actual section for, right, axial section, and this is drawn here to scale. Look at the flange of the beam compared to the web.
Mhm.
Now, you know that if you look here, distribution of the stress is going to be like this, right? Which means this part of the web is not really acting.
Yes.
And don't forget the moment is going to be equal to some force. Let's say that the force distribution is like this, multiplied by the distance from the center to the top. So the distance that you're going to be measuring is going to be from here to any point. So you'd like to figure out the effect of this little segment of the beam web to the column when it comes to the moment. Now we need to take the force developing here. Here's the force, right? So there's going to be, let's say, this is going to be like the, let's say, the tension side, if you like, just to make it simpler for you. Take this tension force multiplied by this distance to give you the moment due to what? Due to the force right here. Compare it with this cross-section area, which is really big, multiplied by this distance from here to there. Which one's larger?
The second
Number one, this is now getting closer to the center of the beam. It's going to be number one. Number two, this cross-section area at this height is going to be very small compared to this cross-section area at this height. Now, this explains to you that most of the force responsible for the flexure, this force here is going to be like tension force. Responsible for the flexure, which means for the moment, is going to be coming from the flange and nothing really from the web. So when it comes to analysis, like for design purposes, this web is ignored when it comes to flexure. And we consider only the flanges. That's why we say most of the tension force is going to be going through the flange of the beam. Now you need to transfer it to the flange of the column.
Okay.
This is the reason.
The continuity plates.
This is why you need the continuity plate. Yeah, right.
Yeah. Okay. That makes sense.
All right.
Oh,
Very good.
thank-
All right.
Great night.
Good night, everyone.
Professor, I have a question also.
Yes, absolutely.
The V gravity, the shear gravity shear, you determined 1.2 D plus 0.5 LL, the live load. Is the live load reduced or just the
No, just the life load doesn't matter. If you
same
wanna,
as the
if you wanna reduce the life load, this is fine, but the tributary area is gonna be very small. So here's the size of bone frame, right? So look at the amount of load that's gonna be coming. It's gonna be coming from through this tributary width, right?
yes?
Okay. So this tributary area is very small. It's not really
Okay.
big.
Okay.
So if you don't really need to reduce it, but if you wanna reduce it, go ahead.
Okay. So in submittal, we don't need to reduce it.
No, you don't have to.
Okay. Oh, that's it. Thank you.
Okay.
Have a good night, Professor.
Good night.
Have also